Okay, let's review what we did yesterday. What did we talk about? Eigen decomposition, no? What is this? So if you have a matrix A, n cross n, what can we do? We can diagonalize this matrix, or we can find a similar matrix which is diagonal. When can we do this? How do we do this? Or what basis do we switch to so that the matrix A, some arbitrary n cross n matrix, looks like a diagonal matrix? Like this? Is it correct? Why is it not correct? You are saying it has to be like this? Which one of these is correct? Second one, is it why? This works with the standard basis. This works with the eigenvector basis or eigenbasis, let's say. So why should it be like this and not like this?
So when we are doing x,
Okay.
x lambda,
Okay.
we are changing this to standard basis.
So what comes out you're saying is in the standard basis.
Standard basis, and then we are taking.
Hey, hold on. Okay, matrix multiplication, the operation is always in this direction, not in this direction. The order in which you're doing stuff is like this.
Basis.
So what goes in here is in what basis? Yeah. So what goes in here is in the standard basis. What comes out is in eigen. This only for stuff to make sense, you should only feed in vectors that whose representation is in the eigenbasis, and what comes out is some transformed version in the eigenbasis. Right. So what needs to go in is in the eigenbasis. What comes out is in the eigenbasis. Now, if you want, you're dealing with standard basis, right? So you do x inverse to go to the eigenbasis. What comes out is in the eigenbasis. You want to go back to the standard basis. So you do this. So this is wrong. This is correct. It's not inverse here. And can you always do this? What is the condition for this to happen? For you to decompose A, what does that mean? Yeah, that's okay. In terms of eigenvectors?
The eigenvectors have to be estimated.
Sorry?
Like all the eigenvectors should be present for the.
Yeah, so you should get a full set of eigenvectors such that they form a basis for Cn. Okay? Alright, and then symmetric matrices. Right, this is for matrices that or okay. What lambda i's are real. We chosen to be okay. That means this also means that you can always express a symmetric matrix. You can always diagonalize a symmetric matrix, and these two will be satisfied. Okay, then right when Jordan form. When you cannot diagonalize a matrix, what you can do is this. This is when would we have a situation where a matrix is not diagonalizable? Sorry? When you have repeated eigenvalues. And yeah, you don't have as many eigenvectors as the number of times this eigenvalue repeats. Okay, all right. And then after this, what are these? What are positive definite matrices? So here again, we're talking about square matrices. And when is the matrix positive definite? What? Right? If this is true for all x not equal to 0, where x is a vector from Rn and the matrix satisfies it, then you say this is a positive definite matrix. But if it's greater than or equal to 0, for some x not equal to 0, then this is positive semi-definite. Okay, all right. Is that where we stopped? Okay, and then we said this is, what is this called? Okay, and then we said, okay, so we said the idea of positive definite matrices comes up in a lot of applications. One of them is in optimization, especially when we are talking about minimizing a function. Okay, and then we're talking about functions of this form. So when you have a function like this, okay, univariate function of one variable, we said that this has a minimum when is a function of this form? Well, df by dx is 0, and we know that this function has a minimum. What if you have a function that is a function of two variables? And the most general form is like this. And I said you can express this in the quadratic form, that you can write it like this. Okay. And I asked you what is A? Okay. So if you write A C like this, okay, and you evaluate this will come out to be this. So you can express this like this. Now, it turns out, well, of course, see whether this function has a minimum or not depends on the values of A, B, and C. Okay. It turns out that the condition for this to have a minimum. See, of course, the first derivatives have to be 0. And then there is an additional condition on the second derivative. There are three possible second derivatives here, right? So you have x1 square, x2 square, and there is a third one. What is the third one? Right. You also have this x2. Okay. It turns out that the condition. So here the condition was very simple. It was only this. But for a function like this to have a minimum, there is a condition that involves all three of them. Okay. Let me try and remember if I can. It's there in the slides. You can derive it by by expressing this in a form, but I can't remember. So there is a condition that relates the three of them. It's there in the slide. You can just refer to the condition. If I remember correctly, the condition is A should be greater than 0, and let me get this, C minus 2B by A greater than 0, or something like this. Okay. So if these two conditions are satisfied, then it turns out that this function has a minimum, and if that is satisfied, it also turns out that A is positive definite. Okay. So this is for the two variable case. Now we can extend this to n variable case, and of course if you try and derive these conditions, it will become unwieldy very quickly. But it turns out that in the general case, when you have a function, if a quadratic function of some vector x is from Rn, okay, this function can be written as in this form, okay, and this function has a minimum when A is positive definite. Okay, and sometimes you will see people write something like this: A greater than 0. Remember, A is a matrix, and I've written it like this. I'm simply overloading the greater than operation to say that this is a positive definite. So when I write a matrix is greater than 0, that simply means it's a positive definite matrix. Okay. Now, in fact, this is a general case. This generalizes even here. Okay. Except now the matrix A is a 1 cross 1 matrix. So I have 4 multiplied by x multiplied by x transpose. These are scalars, so it doesn't matter. That's 4x square. This function has a minimum only when the second derivative is positive. The second derivative is simply this matrix 4, and it's greater than 0. Okay, so that's the most general condition, and the scalar case simply is a special case of the general condition for a quadratic function to have a minimum. That means the quadratic function looks like a ball, okay, or upward facing ball. Okay, and the condition for a matrix A to be positive definite is positive definite if and only if lambda I greater than 0 for all I. Okay, that means all of its eigenvalues have to be greater than 0. Okay. Okay. See, when I wrote this down, I made this implicit assumption that this is a real number. Okay. And when do we, in what kind of matrices do we have eigenvalues that are always real numbers? Right. So this happens only when your A is, okay. In fact, whenever you have an arbitrary matrix A, okay, or the idea of positive definiteness is often discussed only in the context of a symmetric matrix, because this was probably in your assignment where you had to show that any arbitrary matrix can be written as a sum of arbitrary square matrix can be written as a sum of a symmetric matrix and a skew symmetric matrix. Is that right? Okay, right. So you can write it as a sum of symmetric matrix plus sum of a skew symmetric matrix. How do you obtain the symmetric component of this matrix? Do you remember? Half, yes, that's right. Half of what? Right. So if you do this, this will be symmetric. And what about this? Okay. All right. We'll see why we only have to worry about the so if you, when you have an arbitrary matrix like this, the only component that contributes to whether or not the matrix is positive definite is the symmetric component. The skew symmetric component turns out does not add any value here. What is the skew symmetric matrix? When is A skew symmetric? Right, when A equals minus A transpose. Okay. I'll leave this as an exercise for you to verify. If you have a matrix A that is skew symmetric and you take any vector x and you do this will always work out to 0. Okay. This quadratic form, if A is skew symmetric, will always be 0. Okay, you can verify this using this. Okay. If that is the case, if I take this matrix A, okay. Let's say I have this matrix A, I take x transpose. I can write A as a sum of symmetric and the skew symmetric component. X. You multiply this in because of the distributive property. What you will get is x transpose. This is 0. Okay. So we only have to worry about the symmetric component of A. That means no matter what A you give me, all I have to verify is if its symmetric component is positive definite. So if I'm only dealing with the symmetric component, then I only have to compute the eigenvalues of the symmetric component, which will all be real numbers. So as long as they are all positive real number, then you're fine. Then the matrix A is positive definite because its symmetric component is positive definite. Okay. All right. That's all I wanted to say about positive definiteness. The next topic, or a small topic that we'll talk about. So we've talked about norms of vectors. Okay, maybe let's recap. If x is a vector from Rn, what is the expression for the pth norm of x? Okay. Xi. Okay, all right. And x2 is a special case. So this is simply, at least when we are talking about stuff from Rn. Okay. It turns out we can talk about norms of matrices. If you have a set of, let's say we have a matrix, a set of matrices. Yeah. No. So if you have a symmetric matrix, the eigenvalues are real. If for a symmetric matrix all the eigenvalues are greater than 0, then it's positive definite. If it's greater than or equal to 0, then it's positive semi-definite. If it's positive or negative or 0, then you cannot say. Can you give me an example of symmetric matrix with negative eigenvalues? 2 cross 2 matrix. That's all. This is an example of a symmetric matrix that's got negative eigenvalues. Yes. So if you have any arbitrary matrix, you find the symmetric component, find its eigenvalues. Okay. Do these set of vectors form a vector space? Except not vectors, set of matrices. We discussed this in class, no? Do the set of matrices form a vector space? Yes, right? So if you have a bunch of, let's say 3 cross 2 matrices, if you scale them, it remains a 2 cross 3 matrix of real numbers. If you add 2 cross 3 matrices, it will be a 3 cross 2 matrix, you will get a 3 cross 2 matrix. So Or another way to think about this, if A is simply a bunch of numbers arranged in P rows and Q columns, then I might as well think of A as a PQ vector, no? There are PQ numbers here. I can simply write it like this. Right? That means I can define a norm for a matrix using the standard approach that I use, right? Something like this, right? So in fact, you can define the norm of a matrix this way. A popular norm is called Frobenius. It's called the Frobenius norm. This is simply, if you treat this as a PQ vector, it's simply the second norm of the vector, which is nothing but J Aij square. Okay. This will satisfy all the properties that the norm has to satisfy. Okay. So this is one possible norm for a matrix. Okay. However, this one treats your matrix A as simply a bunch of numbers. Okay. But we know matrices have another interpretation, which is that they represent what? What do matrices represent? No. Linear transformation, no? For example, so all these matrices from P cross Q represent what kind of linear transformations? From where to where? Is it RP to RQ? Well, it has to be the other way around. If you have P cross Q, what am I mapping from to where? So you're mapping from RQ to. Okay. Now, because we can also think of matrices like this, there is another way to think about the matrix norms as simply in terms of how much does the matrix amplify okay, I should not call it an input, but I'll call it an input just even though it's not correct. Okay. If A is a mapping from RQ to RP, if I take a vector from RQ to RP, RQ, and I do this, and then I get a vector Y, this belongs to RP. Okay. It turns out, or another useful way of thinking about norms in case of matrices, especially thinking of them as linear transformations from one space to another, is to define the norm of the matrix as simply how much does my matrix A amplify a vector from the input space. Okay, and again, if you're going to talk about how much does it amplify, remember each of this is a Q vector and this is a P vector. Okay, if you're talking about how much does it amplify, then we have to first compress these into a single number and then find out if this has some value 5, does the value that comes out is it 10 or 4.5 or 1 or 0, etc. Right? So you have to have, so if you're talking about amplification of the vector, then first of all you have to now start looking at this at the vectors x and y in terms of how big those vectors are. Okay, and that's essentially the idea of what is called an induced matrix norm. And the simplest way to think about this is a measure of how much does my matrix amplify my vector x from when it takes a vector from the RQ space to the RP space. Okay. Now we know y is x, right? I could now ask, okay, what is the size of y? Okay. Let's say y represents the size of y, x represents, this represents the size of x, the input vector. Okay. Now the norm of this is simply the norm of and we want to identify a number, okay, a positive number C, such that the length of this vector Ax, okay, is always, okay, and this number C essentially tells me how much my matrix A amplifies my vector X, okay, because no matter what vector you take here, what comes out, and whatever size you have here, what comes out is always less than C times the size of the vector that you take. Okay, so C somehow tells you the maximum amount by which your matrix amplifies your sigma. Now, before we proceed, I've simply written down norms here without specifying what norm I'm talking about. It turns out it does not matter what norm you choose. You can choose any of the p norms that you have. Okay, you could have chosen any p norm here, and depending on what p norm you choose here, what you get for this number C, the C will change depending on what p you choose here. That is simply called the pth induced norm. Okay. Or a formal way to define this is you define the pth induced norm like this. Okay. If you have a matrix in vertical line, in between two vertical lines like this, subscript p, this is simply the pth induced norm. This is nothing but the maximum possible value for the ratio, which is Ax pth norm, and this is for all x from Rq. Okay, right. Maybe that's a bit confusing. Let's try and unpack this. Okay, I'll remove this for now. Okay. This is the definition of the pth induced norm. Okay, this simply says, forget about this for now. Take any vector from your input space. Okay, I should not have used P because I also said A is. Let's keep it like this for now. For this particular case, take any vector from Rm, okay, X. Compute the corresponding vector Ax, okay, and then compute their corresponding lengths using the pth norm. Take the ratio. You'll get some number. Okay. Now enumerate all possible ratios you could have gotten depending on whatever x you choose. You have an infinite number of them. The maximum possible value for that ratio is the pth induced norm for your matrix A. That means no matter what Ax I choose, y that comes out, whatever x I choose, the y that comes out will always be less than or equal to the pth norm. Okay. My matrix, so this tells me my matrix A will never amplify this vector x more than this factor. Okay, you're guaranteed that all the vectors will always be smaller than this. Okay, this becomes very useful if you're looking at, let's say, in system analysis. You want to know if the input that you put in, is it going to get amplified or is it going to get smaller and smaller. So this is useful when talking about stability of system. You want to know whether my system amplifies what comes in or does it converge or it does not change. Again, maybe that's maybe a bit too abstract. Or another way to simplify this, we know linear transformations obey scaling property, right? If I scale this by a factor of alpha, the numerator also gets scaled by a factor of alpha. So instead of defining it like this, instead of taking all possible x's, you can also define it like this. You take all possible x's whose pth norm is 1. Okay. And then you simply look at the maximum of this when xp is 1. Okay. This is another definition and both of them are exactly the same. Okay. Okay. See what this means. Now, let's say we have a 2 cross 2 matrix. and we want to find let's say A2. Okay. To do that, let's take this approach. The way you do that is we have P is 2. That means you take all possible input vectors whose second norm is 1. What do those vectors look like in R2? Vectors whose second norm is 1. It's a circle. Right? Now this is all possible vectors. This is 1. Now you choose any vector here, and then you apply A times X. You'll get another vector in R2, maybe like this. You take another vector here, you apply A times R2, maybe you get this. Take another vector, maybe you get this. Okay. So for each possible vector that you can get from here, you'll get a bunch of other vectors. So if this is my input space, if I have a corresponding output space, if I take each of these vectors, I can, if I trace out these points, right, I will similarly trace out some figure here. Okay. It turns out that figure is always an ellipse. Okay. If you choose points from a circle under a linear map, 2 cross 2 map in this particular case, what you will get is an ellipse. Okay. Assuming this is full rank. If it's not full rank, you will get a line. Okay. You can think of that as a compressed ellipse. This is what you get. Okay. So this radius was 1. Now this is what we got. So this is, if this is set of all x's where x equals 1, this is all ax, all possible set of outputs that I get under this map A. Now the second induced norm of this A now is simply the length of the largest vector here. Okay, that's essentially this. Okay, means if I choose any point on this unit circle, I am guaranteed that the vector ax is the second norm of the vector ax will be within the circle. Okay, and the radius of this circle is simply your A2. Okay, that will simply be the length of the major axis of this ellipse. Okay, so that's how you think about it geometrically. Now this is for the second norm. We can do something similar for the, because we can do it for any p norm. Let's see what it is for the first norm. Okay, and before I proceed, let's say A is some matrix. Can you tell me what are the eigenvalues of this matrix? Okay, so the second induced norm for any matrix is simply the square root of the absolute value of lambda max. Okay, so this will simply be the length here will be the absolute value of lambda max. Okay, so for any square matrix A, the second induced norm will simply be this. If you know the eigenvalues, then you know what the second norm is. That means no matter what vector you take here, the vectors will never be amplified more than lambda max. It will always be amplified by a factor lesser than lambda, square root of absolute value of lambda max. Okay. All right. Now, if you have this vector, the same matrix, right? Let's say we are interested in the first induced norm. If we want to find the first induced norm, then where do you choose your input vectors from? Where do you choose your x's from? When we are talking about the second norm, the x vectors were chosen such that the second norm is 1. If you want the first induced norm, your x's have to be chosen so that the first norm is 1. So you have to choose your vector such that this is 1. What does this look like? Or you might see people call this I think this is norm 2 ball. I'm asking you, what is a norm 1 ball? Yeah, it's essentially this. And what are these corners? Well, this is E1, E2 minus E1 minus E2. Yeah, 1, 0, 0, 1, minus 1, 0, 0, minus 1. So, to find the first induced norm for the matrix, you choose all vectors from here, and then you find out what, and then you look at what happens to, if you map this through the transformation A, what do you get here? I've given you the matrix there, you can tell me what it will look like. So you essentially have to find out what happens to this vector, this vector, this vector, and this vector, and then we can draw the figure. What happens to this first vector? Where will it be? This point. Okay, what will be the corresponding vector y when your first vector is 1, 0? No, just the first column. Okay, there will be 2, 1, that will be this point. So this point gets mapped here. What about this? Well, 1, 2, no. 1, 2, it's here. And then this one. Minus 2, minus 1. And this will be. Yes. No, minus 1, minus 2, no?
Minus 1, minus 2.
Right, that's this. So it gets mapped to something like this. Okay. Now, the one norm is the maximum possible one norm that you can have here. Okay. It's a maximum of the norm of all of these possible vectors. The maximum possible norm for these would simply be, so you take this, whatever this is called, this square, this rotated square, and you expand this till that square touches the edges of this, right? So you might get something like this. I'm just guessing. Okay. If you take any vector from here and map it using A, that new figure fits within this, right? That means this is the maximum possible amplification you could have gotten under the first norm. Okay. So the size of this, or this distance here that you have, this will essentially be your, because all vectors under this mapping will have a one norm that is, that essentially fit within this. Okay. And then you can do something similar for the infinity norm, which is again slightly simpler to deal with. Okay. Let's say we are interested in this. That means we need to choose our inputs from, what does that look like? Square where, like this? What is the infinity, norm infinity ball? Okay, but what is the width of the square? If the infinity norm is 1. Width is 1, so minus half to plus half. So width is 2. So this is all vectors. But if you do the mapping, what will you get? So you only have to do the mapping for these and then simply join them by straight lines. What will 1, 1 get mapped to? Well, 3, 3, no? This point will get mapped to here. What will this get mapped to? This is 1, 1. One minus 1. What will this get mapped to? Yeah? Well, just multiply and tell me. So it will be minus 2, minus 1 plus 1, right? Oh, it will get mapped to itself, is it? Okay. So what is this? This is 3. So it's here. This will get mapped to here. Okay. Oh, in fact, minus 1 plus 1 is an eigenvalue of that because this gets mapped to this. Okay. What about minus 1 minus 1? That will get mapped to minus 3 minus 3. It's here. And by symmetry, I think this will be here. Is that okay? So this square will get mapped to parallelogram like this. Okay. What is the smallest box that will fit this? That's essentially this. Right? Bordered at 3 and minus 3. That will fit this figure. Okay. And this size is 3, and that is essentially your. Okay. This means if you take elements from norm infinity ball with norm infinity as 1, sorry, infinity norm is 1, then under the transformation AX, what comes out will definitely stay within an norm infinity ball of size 3. If you take stuff from 1, under the infinity norm, everything will stay within a ball of size 3. Okay? Right. Again, first time you come across this, maybe this is a bit strange, but if you think about it a bit and then do a few examples, then it becomes a little bit more digestible. But finally, I will also see for the second induced norm, we had a nice expression like this. So you could ask, is there a similar expression for these two? It turns out there is. Again, when you see it for the first time, it might sound very strange, but it's after some time it does not feel that strange anymore. So it turns out the first norm is simply you take all the columns of A, okay, and you compute their first norm. Okay. Let's say this is from in this particular. Let's say this is from n cross m. Okay, how many columns do you have? M columns. Okay, that means there are m such numbers that you will get. Okay, and the maximum of all of those, okay, will simply be the first induced norm of a matrix A. Okay, and then this is a bit stranger. Again, A is n cross m. You take the rows of A. Okay, how many rows do we have? N rows, and then you again take their first norm. Okay, and then you take the maximum over I. Remember here I goes from it goes from okay. Okay, all right. Right, that's all I wanted to say for this module. Are there any questions before we discuss the assignment problems? Yes, yeah. Yes,
What does the infinity norm do? I still have doubt.
sure. What is the definition? Do you remember the definition of the infinity norm? Okay, the p. So if you have a vector here, we just write the p norm first. Okay, this was the definition. I'll remove this. Okay. And then, you have a definition like this, and then suddenly somebody comes and says, well, the infinity norm is simply you take all the elements, find their absolute value, whatever is the maximum possible absolute value, that is the infinity norm. Maybe initially this is strange, but it turns out if you think about it a little, it's not that strange. Okay? Now, let's do an example, right? Let's say you have made vector like this. What is the first norm of this vector? In fact, let's catalog it. Let's do it systematically so that this is clarified. So you have x equals 1, 3. We want to find out not all the p norms, but at least some of the p norms. Okay. This is x of p. What is the first norm?
4.
Okay, it's 4. What is the second norm? Can you find out? Sorry?
10.
Root 10. What is root 10? What is this equal to? Something. You have a calculator on your mobile phone. What about 3? You can find out. Some of you can. It's cube root of 28. Okay. Can you tell me what that is? And then let's calculate 10. Or if you can calculate 5. See, this will be 3 point something. This will also be 3 point something. What is square root of 10?
3.16.
16 is it? Okay. Okay, what about the cube root of 28? 3.0? 3. Okay. We'll just do one more. That's 126. What is the fifth root of 126? Okay, 3 point. Okay. What is happening here? Going towards what? It looks like it's going towards something. 3. And what is 3? 3 is the maximum possible number. Okay. In fact, the infinity norm will exactly be 3. Okay. Okay. I've just shown you one example. It does not mean, you understand. But at least I've given you one example instead of no examples. Okay. What is happening here? Right, that's right. Why is that happening? The reason it's happening is here. If you look at this, right, this is simply, now let's forget about 1 by p. Let's raise it to the power p here. Okay. This is simply the sum of x1 power p plus x2 power p xn power p. Okay. Okay. When p is 1, what is the plot of this x raised to the 1? It looks like this, right? Modulus of x raised to the power 1. See, each of these is a real number. I am simply asking what is the plot of the absolute value of a real number. That's this, right? What about this? Right, let's say this is 1, right? This is 1, 1, this is minus 1, and this is 1. What will it look like? It look like this. What about x cube? Well, absolute value of x raised to the power cube. It will look like this. Well, I'm not drawing it properly, but you get the idea. So what happens is, when you look at these terms, right, when you raise it to the power p, if x2 is greater than x1, as the value of p increases, x2 raised to the power p is much larger than x1 raised to the power p. So the amplification that happens, so let's say x1 and x2 have a small difference, but as you keep increasing the value of p, the difference between x1 power p and x2 power p grows further and further. Okay? That means as you increase p, the largest number among them starts to dominate. That means everybody else looks a lot smaller than the largest number here. So if you extend this argument to infinity, that means as you go to infinity, the only number that contributes to the norm is the largest number, and that's the idea. That's why this is in fact logical. This is not some arbitrary thing that people have pulled out. If you extend this, if you keep increasing this p, this number will always tend to the maximum possible absolute value of its elements. Okay? So that's the infinity. I mean, this is again a reasonable measure of a size of a vector. I mean, these are all possible measures of size of a vector. One possible size is what is the largest number. If you have two vectors, I'll say the vector with the largest possible individual value in the different values it has is the larger vector. That's one way of measuring distance. Okay. Okay. Are there any other questions? No? Okay. All right. There were 3 problems people had asked about. See, the first one is very easy. This question of finding out a power 10 or a power 100. Why? I don't know who asked. Okay, A is something like this. It's got some B matrix, some diagonal matrix, and C. If you had simply found out A square, right, you would have observed that A and B are inverses of each other. That means if I do A square, then I have B lambda C, B lambda C, B and C are gone. So what you effectively get is, so if you want to know A power n, all you have to do is find lambda power n and multiply it by B and C on either side. In fact, if you have a matrix A that can be diagonalized, you can easily find what is A power n. What is A power n now? Well, it's simply the power 1. Okay, that is, so this is easy. The second problem, there are some issues with the problem which we will address, but I will simply talk about the general principle. So the problem was, if you have, let's say, differential equation like this that you need to solve, the question was to use whether we can express this as a set of linear equations, so solving this, okay, numerically. Okay, and the way you do this, for example, let's say you want to compute this for values of x starting from some value a to b. These are the possible values of x. Okay, and the way you solve this numerically is you divide your into uniform intervals of size delta x. Okay, and let's say we call this I equals 0, this is I equals 1, 2, 3, 4, and let's say this is I equals n. Okay, that means we will define x I as a plus I times delta x. Delta x is your step size. This is the step size of your integration. This is your xi. Okay. And to be able to solve this numerically, you have to find an approximation for the derivative. What is the derivative of a function? What is the definition of a derivative of a function? So if you have a function f of x, how is its derivative defined? Well, if you remember this, it was defined something like this, right? Okay. If you have a curve like this, if you want to find the derivative at this point, this is your x, this is your f of x. You find a point that is close by x plus delta x. The value here is f of x plus delta x. Value here is f of x. You find this difference and you take this difference and you take their ratio. That's this. This is delta x, this difference is delta x, this difference is f of x plus delta x minus f of x. That's the numerator. If you take this ratio, you get some number. Okay. If the function has a derivative at this point x, it turns out that if you bring this delta, if you make this delta x smaller and smaller, okay, that means instead of taking it here, you take it here, and then you compute this ratio, you'll get another number. You'll not get the same number unless it's a straight line. If you keep bringing it closer and closer, you'll get a bunch of numbers. Okay, it turns out that sequence of numbers will converge to one value, like what happened there. See, these numbers looks like they're tending towards 3. If you do something similar here by changing the value of delta x, by continuously decreasing delta of x, that's what you're saying here. If you keep reducing delta x to 0, these ratios will converge towards a value, and that value is simply the derivative of your function. Okay, that's the definition of the derivative of function. Of course, we can't afford to have 0 delta x, so we say, okay, we don't have to worry about making delta x too small. Maybe for my application, a chosen delta x is small enough, right? So we instead of using the true definition of the derivative, we say the definition of derivative for us is simply this, without worrying about taking delta x to 0. We simply choose a delta x which we think is small enough, and we compute this. Okay, you have a function, you compute f of x, you compute f of x plus delta x, take the difference divided by x. That's a good approximation of your derivative. Okay? So if you have a derivative like this, then dy by dx can simply be written as the value of y at x plus delta x minus divided by. Okay, before we proceed further, I need to maybe step back a little and then give the big picture. Now, if you're dealing with differential equations like this, then you're dealing with a continuous variable x and the continuous variable y. Okay, we don't know. Let's say we don't know how to solve this analytically, so we want to resort to a numerical way of solving this. That means, if you want to take up a numerical approach to solving this, what you will get as an output is not some analytical function for y, but the reasonable approximation for the values of y at these different values of x. Okay, because if we solve this, right, what you will get as y will be a function of x. Okay, we can't find an analytical expression for y of x, but what we can do is, by approximating your derivative in this form, you can compute what, let's say, if you had solved this, you would have gotten a function y of x. If you had solved this analytically, maybe you get a function like this. But we don't know how to get this. Okay, but we know what is f of x, so we say we'll do it numerically. When you do numerically, what you will not get this. What you will get is the value of this function at specific points, at specific values of x. Okay, you get to choose what the specific values of x are. So here we choose the values of x for which we want to know y of x are are these points where x equals a plus delta x, a plus 2 delta x, a plus 3 delta x, so on and so forth, till x equals b. Okay. So if you were to solve this numerically, what you will get is a bunch of values, in fact 0, n plus 1 values, that will, where each value of that output will tell you something about the solution to this original equation. Okay. So what you want to get out of this, this numerical procedure, is the value of the function at y naught, which is nothing but where y of a, or where x is a, or equals a. y1 is the value of the function when x is a plus delta x. y2 is a plus 2 delta x, and so on and so forth. Essentially, this value, these values. Okay. Now, if we are lucky enough and we choose our delta x appropriately and f of x is fairly well behaved, then you get a good approximation of solution. If f of x is not well behaved and you choose delta x to be, if you don't choose delta x to be an appropriate value, then what you get might not be a good approximation. Okay. Okay. So what we finally want out of this procedure is a bunch of numbers like this, which are a good approximation of my original y, my solution y of x. Okay. Now, how do we go about doing this? Okay. The first thing you do is you approximate the derivative y dash. See, this we can compute. So we approximate y dash in terms of the value of the function that we can compute. Okay. So that means we say the derivative of the function at x equals a is simply this difference divided by delta x. Okay. So at x equals a or I equals 0, my derivative y dash of x equals a is approximated as, what is it? The value of the function at x equals a plus delta x minus the value of the function at x equals a divided by delta x. That will be y of a plus delta x minus y of a divided by delta x. This is my approximation for my derivative. Okay, but my differential equation says that this is equal to f of x. F of x I know because this is my input. That means this is equal to f of x. Y of a plus delta x minus y of a equals f of x. Otherwise, I can write it as, well, x here is a, so this is f of a delta of x. Okay, what is y of a plus delta of x? I've defined it to be y1, and this is y0. That means y1 minus y0 is f of a delta of x. That is at the first point. Now I move to the second point. At the second point, y dash equals f of x. That means y dash equals f of x, f of a plus delta x. What is the approximation of y dash when x is x a plus delta x? Well, use the same approach or this approach. The approximation for the derivative y dash at x equals a plus delta x, this is approximately equal to y2 minus y1 divided by delta x. I have not written, that's because here it's a plus delta x. That means this will be y of a plus 2 delta x minus y of a plus delta x, which is simply a2, y2 and y1. This will be equal to what? F of a plus x. So that means this is equal to you simply, oh I see. Oh. That means now now we've done it for this. You simply do this for all the possible values till x equals b. That means you get a bunch of linear equations where the right hand side you know f of x, You've chosen delta of x. What you don't know are y1, y2 up to yn. That means if you, but we do know one thing, right? It's a differential equation. To solve this, you need initial condition. We know, let's say, y of x equals a is 0. Okay. Then it simply means if you collect all your unknowns, your function that you're trying to compute, right? We know y0 is 0. Okay. Well, that's all we know. If I stick a matrix here and I do this, so write it like this. Forget about what is here. We don't know. At least the first line, first row should make sense. If you multiply this with this, you will get y0 equals 0, which is given, which is the initial condition. Okay. So that's, what about the second one? Second one, we can use this. Okay. y1 minus y0 is fa times delta of x. The right hand side we know. So this is f of a times delta of x. What will be this? This will simply be y1 minus y0. That means I take minus 1 times y0, 1 times y1. That gives me this. What about the next one? Next one is here. Minus 1, 1, 0, 0, and this will be equal to f of a plus delta x. And you simply write it down. Okay. What you will have then is, well, if you simply solve this, you'll get you've essentially done integration. That's all. You've essentially done integral of x dx to get y. Okay. This is for the first derivative. What if you had something like this? Well, we can take the same approach. If the first derivative of y is approximated like this, then the second derivative of y maybe can be approximated as the value of the first derivative of x, y at delta x minus first derivative of x divided by delta x. But we know we have an approximation for each of these, right? What is the approximation of this? This is y of x plus 2 delta x minus y of x plus delta x minus this minus y of x plus x minus x divided by delta x. But remember, each of these has the delta x in the denominator, right? Here. That means this will become square, and essentially your y double dash will be approximated by x plus 2 x minus 2 times y of x plus delta x plus y of x divided by square. Now we simply use, so if this is what you want to solve, at each value of x where you want to compute your y, you find and you use this as an approximation for your second derivative, and then you will get a bunch of linear equations that you can express like this and then solve. Okay. Except here, because there are two derivatives, you need two initial conditions. Let's assume a equals y dash of a equals 0, where a is the initial value of x from which we want to start computing this function. Okay, this is what you do. This is the approach. Okay. Okay. We are out of time. The other problem we'll discuss it next Monday. Yeah. That's all.